The James Webb Space Telescope, moreover known as Webb or JWST, is a reliable pioneer that has uncovered astounding pieces of information concerning stars, planets, universes, and other entrancing boundless eccentricities, as well as setting new guidelines for scientific energy. Webb is hailed as the regarded Hubble Space Telescope substitution. People, starting with one side of the planet then onto the next, are trading photographs or utilizing crude information to make new revelations. Just 3 minutes ago, James Webb captured the most astonishing picture ever found in history. 1 year has passed since the amazing James Webb Space Telescope unveiled its absolute first vital picture of the universe, stunning stargazers across the world with its superb detail. Yet its latest finding is a shocking image of the universe that we have never seen before. What has been seen up to this point by the James Webb Space Telescope is uncovering more forward leaps than it managed. Researchers say the substitution to the Hubble scope uncovered new data about star development, universe blends, and the early universe. Only 1 month after the underlying photographs were delivered, the photos were astonishing, revealing the universe thoroughly. From that point forward, the quantity of exposures has taken off, giving researchers a gigantic information motherlode. James Webb Space Telescope's pictures of grandiose tarantulas, record-breaking space smoke, stars, and other wonderful, brilliant articles have been documented. This satellite observatory's top-tier headways permit us to peer farther into space than prior, revealing previously dim subtleties about the universe. As a method of reviewing the principal year of the James Webb Space Telescope's movement, NASA delivered a picture showing a small star-forming local in the Rucci Cloud Complex. The picture shows planes shooting from child stars as enormous development floods of different assortments influence atomic hydrogen, which makes up the red development. The presence of a circumstellar circle makes a few theories around a couple of stars, suggesting the chance of planet arrangement in the far-off past. The picture could show noteworthy turmoil, yet as per NASA, this sublime nursery is small and quiet compared to others. The vigorous stars in this district are about the size of our Sun or considerably more modest, making it the closest star-forming area to Earth. This image was caught by the essential camera of the observatory, the Webb Space Telescope's close-in camera, which catches staggering pictures in 2 unmistakable infrared ranges. Additionally, the Space Telescope has improved how we might interpret exoplanets, or planets that circle stars other than our Sun. James Webb is especially skilled at concentrating on far-off monstrous universes. The satellite observatory found its first exoplanet, LHS 475b, toward the start of 2023. The planet is 41 light-years away and has a width similar to Earth's. James Webb, as per NASA, is the main functional telescope fit for sequencing the environment of Earth-sized exoplanets. The disclosures delineated how exact the telescope was. Exoplanets are presently another frontier for cosmologists to investigate. The James Webb Telescope likewise found proof of old systems that, according to a hypothetical viewpoint, shouldn't have existed. The Advancement Lab of Swindon School and its inestimable group have found 6 legendary old cosmic systems called universe breakers, which could fundamentally affect how we might interpret space. These epic worlds could have showed up between 500 to 700 million years after the Big Bang, as per the specialist results. Recently, the telescope's infrared sensors distinguished them, permitting us to think back in time around 13.5 billion years when stars and universes were substantially more settled. The huge size of the universe breakers has left researchers confused. Cosmic systems in the early universe ought to have been 10 to multiple times less than their EB and current size. These 6 articles might be billions of times heavier than our Sun, and the general mass of stars in a solitary system could be 100 billion times heavier than our Sun. Attempting to fathom something so monstrous causes you to feel awkward in spite of mechanical progressions. Planets that are very huge to exist have specialists confounded. None more so than the revelation of a planet remembered to be excessively monstrous for its star. This has prompted a reassessment of our whole comprehension of planet arrangement and planetary framework plan. A planet that is roughly as extensive as Earth has been seen by research from Pat 8 Tails, which suggests that this planet is in a planetary framework around the ultracool star LHS 3154, a star that is ordinarily more modest than our Sun. Before actually seeing it for themselves, researchers didn't think such a circumstance was conceivable, Yet new proof shows that the largest planet in our planetary framework is indeed circling one of the universe's littlest, coolest stars, the ultra-cool dwarf. We still have practically no comprehension of the universe. This disclosure shows that a planet of this mass circling a star with such a low mass overcomes our presumption. These stars could have formed an immense gas and residue mist, and planets could arise from the gas and residue that stay in the plate of material around the infant star. However, it isn't conjectured that the planet-forming plates around the low-mass star LHS 3154 contain sufficient solid mass to create this planet. By and by, it exists, so we should now reevaluate our speculations about heavenly and planetary development. A decent relationship is balanced. A star with an outer intensity source should keep up with its interior temperature. You really want to draw nearer to the intensity source as its temperature diminishes. Planets are the very planets that ought to be sufficiently warm to support fluid water and should be nearer to their stars. For instance, Earth is in the livable zone due to the glow and light it gets from the sun. The distances of different planets from our sun are either excessively perfect or excessively little for them to get the perfect proportion of light to support life. Presently envision a universe with a much cooler star. Drawing nearer to the fire would be comparative for planets circling a cold star to get the perfect proportion of energy to support life. The planet size ought to likewise be changed in accordance with give the best distance to energy and light to support life. Getting back to our past conversation, there are various speculations for why the planet might have formed close to the little star. As per a widely held conviction, the planet could have been a lot larger at first. Over the long haul, the planet would have lost a lot of its mass. However, this hypothesis has a significant blemish since enormous mass makes a planet lose a larger number of gases than solids. In this case, it is guessed that a large portion of the planet's mass would have been gases, which is conflicting with the finding. One more clarification is that this enormous planet formed a long way from the little star. Assuming the planet had the option to try not to get a lot of light, it would probably be ice-covered. The star could ultimately gravitate toward this far-off planet, resulting in this monstrous planet being near the little star. In spite of the fact that there is a chance that the two thoughts could make sense of the planet-star pair, researchers are as yet unable to completely comprehend the irregularity. With cutting-edge technology like JWST, analysts are currently looking at planetary frameworks more meticulously, and each new finding is pushing them forward. We have dug all the more profoundly into how the universe has formed over the course of the last few decades than we have over the most recent 30 years. The tremendous measure of information provided by the telescope has previously prompted major logical advances that have flabbergasted space experts and ignited revenue in future space investigation. With the James Webb Space Telescope in operation for a year now, one thing is sure: the universe is undeniably more perplexing than we previously envisioned, and there are many inquiries we presently can't seem to answer. The James Webb Space Telescope, JWST, sent off by NASA in December 2021, addresses a fantastic jump forward in our mission to comprehend the universe. Named as the replacement to the Hubble Space Telescope, JWST is furnished with trend-setting innovations intended to catch phenomenal perspectives on the universe across a more extensive range than any time in recent memory. At the core of JWST's capacities is its huge essential mirror, bragging a breadth of 6.5 meters, 21.3 feet. This size is over 2 times that of Hubble's mirror, permitting JWST to gather and shine altogether more light. This expanded light-gathering power empowers JWST to notice finer and more far-off objects with excellent clearness and detail. One of JWST's key instruments is the near-infrared camera NIRCam, fundamental for noticing the universe in the infrared range. Infrared light is significant for concentrating on heavenly articles since it enters grandiose residue mists that block noticeable light, uncovering stowed-away stars, cosmic systems, and planetary frameworks. NIRCam works in 2 infrared frequencies at the same time, giving cosmologists important information on the temperatures, compositions, and developments of far-off divine bodies. Another basic instrument on board JWST is the near-infrared spectrograph, NIRSpec, which disperses light from far-off objects into its part tones or spectra. By breaking down these spectra, stargazers can decide the compound composition, temperature, and movement of stars, worlds, and exoplanets across immense distances. This ability is priceless for concentrating on the development of stars, the advancement of planetary frameworks, and the climates of exoplanets. JWST's mid-infrared instrument, MIRI, supplements NIRCam and NIRSpec by zeroing in on considerably longer infrared frequencies, fundamental for concentrating on the coolest objects known to man. MIRI's high-level locators and spectrographs empower definite perceptions of cold gas mists, dust-covered star-forming locals, and the warm emanations from far-off planets. Along with NIRCam and NIRSpec, MIRI provides a comprehensive view of the universe across an expansive range of infrared frequencies. One of the most anticipated capabilities of JWST is its capacity to review exoplanets, or planets circling stars beyond our planetary group. JWST's powerful instruments permit cosmologists to examine the atmospheres of exoplanets as they pass before their host stars, a procedure known as transit spectroscopy. By measuring the changes in starlight passing through an exoplanet's atmosphere, JWST can detect gases like water vapor, carbon dioxide, and methane, providing insights into the planet's atmospheric composition and potential habitability. In addition to its scientific instruments, JWST's orbit around the second L2 range point, roughly 1.5 million kilometers, 930,000 miles, from Earth, ensures minimal interference from Earth's atmosphere and heat. This stable vantage point allows JWST to maintain a consistently cold temperature essential for its infrared observations and provides continuous views of the universe for extended periods. The journey to launch JWST has been a decade in the making, with global cooperation among NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Each agency contributed significant expertise and innovation to the telescope's development, ensuring its success as a global endeavor in space exploration. Scientifically, JWST aims to resolve fundamental questions about the universe's origins, development, and creation. By observing the universe in infrared light, JWST can peer through vast dust clouds, study star and galaxy formation, and explore the conditions necessary for planets to form and support life. These observations will build upon the discoveries of past telescopes like Hubble and transform our understanding of the universe. One of JWST's primary scientific objectives is to study the first stars and galaxies that formed in the early universe. By detecting the faint infrared light emitted by these ancient objects, JWST can probe further back in time than ever before, unraveling the mysteries of how the universe evolved from a hot, dense state to one filled with stars, galaxies, and eventually planets. Another key area of investigation for JWST is the study of star formation and planetary systems within our own Milky Way galaxy. JWST's high-resolution imaging capabilities allow astronomers to observe protostars, the precursors to stars, embedded within dense gas clouds. These observations provide insights into the processes that drive star formation and the evolution of planetary systems around young stars. Additionally, JWST's observations of planetary systems beyond our solar system offer a glimpse into the diversity of exoplanets and their potential for habitability. By studying the atmospheres of exoplanets, JWST can identify chemical signatures that might indicate the presence of life-supporting conditions, such as liquid water or organic molecules. These discoveries will inform future research and missions aimed at finding Earth-like planets capable of supporting life. Beyond its scientific goals, JWST represents a technological marvel in space engineering and instrumentation. The telescope's intricate deployment sequence, including the unfolding of its segmented mirror and sunshield, required precise engineering and testing to ensure successful operation in space. JWST's instruments underwent rigorous testing to withstand the harsh conditions of space, including extreme temperatures, vacuum conditions, and radiation exposure. The development of JWST also pushed the boundaries of international collaboration in space exploration. Researchers and engineers from around the world contributed to the telescope's design, development, and testing, leveraging expertise in optics, material science, advanced engineering, and astronomy. This collaborative effort ensured that JWST would achieve its scientific objectives and pave the way for future space missions. Looking forward, JWST promises to revolutionize our understanding of the universe and inspire future generations of astronomers, scientists, and space explorers. The telescope's extraordinary capabilities will enable discoveries that were once thought impossible, from unraveling the mysteries of dark matter and dark energy to studying the atmospheres of distant exoplanets. Moreover, JWST's findings will have profound implications for our understanding of Earth's place in the cosmos and our potential for life beyond our solar system. In summary, the James Webb Space Telescope stands at the forefront of 21st century cosmology, poised to reshape our understanding of the universe. With its advanced instruments, global collaboration, and ambitious scientific goals, JWST represents a testament to human ingenuity and curiosity about the cosmos. As JWST embarks on its journey of exploration, it holds the promise of uncovering new revelations, addressing key questions about our origins and existence, and inspiring future generations to explore the wonders of the universe firsthand.